expects you to know in terms of momentum, being able to define momentum and impulse, determine impulse due to a time-varying force on a force time graph, law of conservation of momentum, and solving problems. So that's our goal for today. But before we get started, let's just talk about it. Momentum is a term that you hear all the time, particularly if you play or watch sports. We talk about it all the time. So I think we have kind of an intuitive understanding of what momentum means. So what does it mean? For you guys, what are we talking about when we say momentum?
It's like extra force.
Excellent. Okay. Okay. Force, power, can't stop easily, right?
It's resisting you.
Movement.
It's resisting you to change in acceleration.
Excellent. Resisting, it's kind of like inertia then, resisting a change in acceleration. It has to do with all those. And so intuitively you have a kind of a gut feeling for what we're talking about. It's something that you possess, it has to do with forces and movement and power. And when you have it, it's hard to change it, right? I mean, when the momentum's going with you, for some reason, it's going with you. You know what I mean? And it's good, right? But when the momentum's against you, that's a bad thing, okay? It's like you're swimming upstream. Exactly, okay? So it's like, you guys know what a Mack truck is? Big, giant truck, right? Big, like dump trucky kind of thing, huge. And a little skateboard. So you can picture those two things. Which one has the most momentum? Okay. Truck depends on how fast it is. Okay. You don't have enough. So what more information would you like to have? Okay, great. But a lot of times people will say, oh, the Mack truck has more momentum. And why would you assume that? Because it's bigger. Excellent. So momentum must have something to do with how massive an object is, as well as with its motion, correct? Great. Is it possible for the skateboard to have more momentum than a Mack truck?
Yeah.
Give me an example how. That's a real simple one, right? If the Mack truck is motionless, does it have momentum? No. So even just a rolling skateboard would have more momentum than a Mack truck then. But generally speaking, if both of them are moving, the truck's going to have more momentum, right? Okay. Mathematically, you guys, momentum is very, very simple in terms of physics. We define momentum with the letter P, which is strange, but get used to that. When you see the letter P in an equation, it stands for momentum. And we calculate momentum by taking the mass of an object times its velocity. That's it. That's so easy. I love it.
But it's just the mass times velocity.
Mass times velocity. That is momentum.
Like,
Kind of like force, except force is mass times acceleration. But here, so mass times velocity, momentum. What's the unit? What's the unit we measure mass in? Kilograms. Please remember that. The unit we measure velocity in? Meters per second. Therefore, what's the unit for momentum? Kilograms meters per second. We don't have a new name for it. We just call it kilograms meters per second. I have 14 kilogram meters per second of momentum. It's kind of hard to say, but that's what we do. Now, again, it's a product of mass and velocity. Obviously, if something has a huge mass and it's moving, it's going to have a lot of momentum. And an example is like an ocean freighter. Have you guys ever been out in like shipping lanes or near shipping lanes where you've seen those huge ocean freighters we use to ship oil and goods across the world? Have you ever seen those things? They are enormous. They're enormous. And when they're scary enormous. And when for example, a fully loaded oil tanker, when it's out in the shipping lanes going full speed, when it's coming to port, they actually put it into neutral 15 miles away. That's how much momentum they have, because they will coast through the ocean for 15 miles with no power whatsoever. That's a lot of momentum, okay? You absolutely do not, because they're moving faster than you think. And if they needed to stop, let's say you had a little motorboat and you're screwing around out there in the shipping lanes, woohoo, and like your motor breaks. Oh my gosh! And you're sitting there, and here comes the super tanker, and the captain happens to see you, and he puts it into full reverse. It'll take 3 miles to stop. 3 miles, okay? Before it stops, exactly. You'll be dead. Forget about it. Forget about it. Okay, let's talk about the impulse momentum theorem, okay? The impulse momentum theorem. This is a pretty simple concept. In words, basically, the way it's written is that an impulse causes a change in momentum. That's pretty simple. So then we need to know what an impulse is. And again, intuitively, if you think about it, you can probably figure it out. What do you do to make something change its momentum? You change acceleration by doing what? Adding a force or exerting a force, right? So if you apply a force to an object, you will change its momentum. So therefore, impulse must have something to do with force, okay? Not necessarily. You can do it in the same direction and increase its momentum in that direction, right? So here it is. An impulse is a force exerted through a time interval. And we do that mathematically by taking force times time. The force on an object times the time that force is being exerted is called impulse. And that will cause an object to change its velocity, which is basically a change in momentum. Force, F is force, T is time. So force times time is what we call impulse. And mass times velocity is what we call momentum. And this is the impulse momentum theorem. Now really, this is just a restatement of Newton's second law, and I'll show that to you in just a second. But I want you to look at this for a second. So we say if I apply an impulse, I'll change momentum. And I can change momentum by changing velocity. Is there another way I could change momentum of an object? Yeah, you could change the mass of an object. In this class, we normally won't do that because it gets a little tricky, but sometimes that happens. Think about rocket science for a second. Imagine a rocket, okay, that's carrying fuel and being launched into space. As it's, okay, so it's accelerating, its velocity is changing as it's going up, and at the same time, the fuel is being burned. So two things are happening. It's changing its velocity and its mass at the same time. Its momentum is constantly changing, okay? That is totally manageable with a tool called calculus, which we don't do with this class. But so in this class, we're going to usually have a constant mass and a changing velocity. So here's the impulse momentum theorem, right? Impulse momentum theorem. Check this out. Watch what we can do. I'm going to rearrange this equation. Okay? Which then I can make this out of. And what's delta V over T? That's acceleration. Okay? So really, the impulse momentum theorem is really a statement of Newton's second law. And actually, Newton did not write his second law, F equals ma, even though that's what we call it today. He actually wrote it in terms of momentum. But he didn't call it momentum back then. They called it property of motion or something like that, the property of motion of an object, which we call momentum. And so in your data booklet, you'll notice that you have an equation, and please double check for me, but I think, what form is it? I think it's this equation here. F equals delta P over T. I believe that's in your data booklet, right? So, okay, great. Okay, so please recognize this is where it came from. That is the impulse momentum theorem, that a force causes a change in momentum over a time interval. It's just another statement of Newton's second law. So let's think about this impulse momentum theorem because it's a really useful tool. So the impulse momentum theorem. Imagine you are going out hunting squirrels with your bow and arrow, okay? Primitive squirrel hunting, right? And you see a big fat squirrel in the tree, and you're going to shoot your arrow at it. And you decide that it's not that big of an animal, so I don't need to really draw my bow back very far. I'm just going to draw it back, a little bit. And you release it. What's your arrow going to do? Okay. Why do you pull the bow back further? What's the whole point in terms of the impulse momentum theorem? What's the purpose? You get more velocity, but why?
Because it's the force of the bow.
Yeah? Why is the impulse larger if you draw the bow back farther?
Because there's less time.
The force that the string is exerting on the arrow, it does it for a longer time interval, right? It's a greater time. So since the force is being applied for more time, there's a bigger change in momentum of the arrow, which means a greater velocity, okay? Think about playing tennis or golf or baseball or hockey, okay? You want to hit the object and you want to hit it hard and fast. What do coaches always tell you to do? Bless you. Okay, tennis, you're going for a big forehand. Do you go like this and stop? Follow through. Why do you follow through?
Because then you enact
More time. The more time you can exert a force, the greater the impulse, which means a greater change in momentum for the object. Okay? Yeah, I think that's about all I want to say for that one. Okay, so those are ideas for how to increase momentum. But we can also look at the impulse momentum theorem in a different way. Here I have an egg. It's a raw egg. If I drop it, it will break. If I take this egg and throw it against the wall, what will happen? It'll break. If I take this egg and throw it against a sheet, what happens?
It'll break.
Why does it not break? Okay?
There's less time. Because if it absorbs it, it means
Okay? Let's think. It's like the egg toss. Let's think about the impulse momentum theorem. Does the egg have momentum when it's flying through the air? Does it change its momentum when it comes to rest? Okay, so the change in momentum will be the same no matter how, because it's going from having momentum to having no momentum, right? So this change is constant. What's the difference between changing its momentum against a wall versus against a sheet?
the wall is time.
The time. If I make, if I have a certain change in momentum, that's a given. A change in momentum is going to happen. If I do that change in a very large time interval, it takes less force. If I do that change in a very small time interval, it takes more force. Exactly what Robbie's saying. Would you rather fall off of a cliff and land on a big soft pillow or land on concrete? Well, the soft pillow is nicer because it brings you to rest over a greater time interval. Therefore, there's less force involved. No, the change in momentum can still be the same, but you're doing it with less force because you're doing it with more time. This is why you wear seat belts. This is the number one reason why you wear your seat belt, okay? Because here's your car, okay? And you're driving along at a nice clip, and you're getting ready to crash into a wall, okay? Ooh, that's bad, okay? Now, if you're not wearing your seatbelt, when your car hits the wall, what does your body do? Keeps going. You have inertia. It wants to continue at that same speed until something impels it to change. And if you're not wearing a seatbelt, what's going to impel it to change? Okay? First the steering wheel, and then the windshield, okay? And they will stop you very rapidly and very painfully. But if you're wearing your seatbelt, you are part of the car. You're attached to the frame of the car. And as soon as the car hits the wall, the car begins to crumple and slow down. And you begin to slow down with it. So really, it's helpful that it prevents you from flying out of the car. That's nice. But the real thing the seatbelt is doing is increasing the time interval in which you come to rest. And even though it doesn't seem like it would be much, if you did the math and looked at it, it's a very significant difference. And and the airbag is even better yet. Exactly. The airbag is doing exactly the same thing. It's increasing the time interval you come to rest, therefore decreasing the force it's needed. Okay. Oh, it still hurts. Don't get me wrong. It hurts a lot less than hitting the steering wheel, though. Oh yeah, you'll still get bruised and stuff, but you won't be dead, which is nice. Now, so think about this. You're driving your car, and you're gonna crash. Oh my God, I'm gonna crash. And I've got two choices. This is awesome. Sometimes you have a choice. I can run right into that cliff over there and crash, or I can swerve off the road, down this embankment, through a field, tumble, flip a few times, and come to rest over there in the cornfield. Which one are you gonna do? No cliff. Right. So if you have a choice to increase the time interval that you are going to crash, that's better because it takes less force to stop you. It's less forceful. It's better. Okay? Exactly. So here's what we're talking about. Increasing momentum, decreasing force, and crashing cars. Let's talk a little bit about bouncing versus stopping and how momentum changes. And we'll demonstrate that with our magical happy and sad balls. So here's our happy ball. And the thing about the happy ball, we notice that it bounces, okay? And our sad one, he falls and sticks, okay? So the question is now, which ball experiences the greater force? The happy ball or the sad ball? Which one experiences the greater force? Think about it. Sad, happy. Oh, I hear both. Happy, sad, okay? Let's look at the question then in terms of the impulse momentum theorem. Okay? Which one has a greater change in velocity? The happy's got a certain velocity here, and then it has, let's say, the opposite velocity, the same, for a change of 2v, right? This one's got a v, and here it's got 0 for a change of just plain old v. I know that's I know. So does that make sense, though? So the happy ball actually has a greater change in velocity. Which one has a greater change in momentum, then? Assuming they have the same mass. The happy one. Therefore, which one experiences a greater force, assuming that they are in contact for the same time period? The happy one. A greater change in momentum over the same time interval equals a greater force. Okay? Think about this in terms of snowball fighting, right? You're in a snowball fight, and the snowball's coming at you. Would you rather have the snowball hit you and stick or hit you and bounce off of you? You'd rather have it stick to you, because if it hits you and bounces off, it hurts more. It's more force. Yeah, because it's a greater change in momentum. Conservation of momentum. Okay. This is one of the, we've talked about Newton's second law, F equals ma, as being a really important equation, and it really, really is. But there are a couple of laws in physics that are immensely powerful and immensely important, and this is one of them. It's called the law of conservation of momentum. You'll see another conservation law when we talk about energy next week, called the law of conservation of energy. This is the law of conservation of momentum. What does conservation mean? To keep it the same, or to save, or to conserve. Doesn't change. Doesn't go with it. Correct. Momentum is kind of the same way. Momentum cannot be created or destroyed. That's basically the law of conservation of momentum. And it says, that the total momentum of any isolated system is constant. It cannot change. Okay? Now, in order to understand this, we need to know what an isolated system is. And a system is anything you want it to be. Okay? You can study something and say, this is my system. Like, I could be looking at an atom, and that could be my system. I could be looking at a container of gas. That's my system. I could look at all you guys, and you could be a system. The solar system is a system. The universe could be a system. Whatever you want, whatever you're studying is your system. And we say a system is isolated if there is no energy entering or leaving, and there's no matter entering or leaving. Then we have an isolated system. Okay? It's isolated from the rest of the world. And if a system is truly isolated, then the total momentum of that system cannot change. It must stay constant. So this is a really powerful tool. We will use it quite a bit. But let's first just think about angular momentum, and back to the first day of class with that spinning student trick that we did. Now, remember I had someone with what masses, and were you standing? Okay, standing. Was it on a chair? I can't remember because the thing broke. Okay. So anyway, but you know what I'm talking about. You held your masses, spin you, and you start spinning faster. Well, that has to do with angular momentum. And what we're talking about is linear momentum, which is momentum of an object in a straight line. But if something is rotating, it also has rotational momentum, what we call angular momentum. The only difference between linear momentum and angular momentum is we add one more factor to the equation. You don't really need to know the equation, but I want you to think about it for a second here. The equation for angular momentum looks an awful lot like linear momentum. There's linear momentum. But with angular, I add the radius of the rotating object, okay? So here you are, either an ice skater or you're in my class doing the thing at the beginning, okay? You're holding these masses, and I get you spinning. So you have angular momentum. And angular momentum in an isolated system has to be conserved, just like anything else. When you bring your arms in, you have decreased your radius. You've decreased the radius of the spinning object. In order to conserve momentum, what has to happen? Either your mass changes, which doesn't, so therefore your velocity must increase. your rotational velocity must increase to conserve momentum. That's why you spin faster, law of conservation of momentum. Okay? Now here's a weird thing. For me, the law of conservation of momentum is easy to apply, and so I always struggle teaching it because a lot of times kids really have a hard time with it, and I can't figure out why. So you're going to have to kind of help me with this one. But let's imagine we have two balls flying towards each other, and this is an isolated system. There's no outside energy being added or removed. There's no other balls in this situation. And what the law of conservation of momentum says is that the momentum I have up here has to equal the momentum I have down here. It can't disappear. It can't go away. Okay? You're right. We're talking about the total momentum. So if I know the momentum of this object plus the momentum of this object, that will be equal to the momentum here plus the momentum here. We're not talking about velocity now. We're talking about momentum, okay? Yes. So in this particular case, if I was to solve this problem, what I would do is I'd say, hey, my initial momentum has to be equal to my final momentum. Okay? That's it. And then I'd usually have some numbers. I could plug them in there. We could try it and figure it out. Okay? It's pretty simple. But it's not always this simple because you have to analyze the situation. So, for example, well, let's see. Let me go to the next slide here. Okay. So, in most simplistic form, there's the law of conservation of momentum. The momentum before a collision or before an explosion has to equal the momentum afterwards. It could look something like this. That's the one we just talked about. But it doesn't always have to look like that. It could look like this. I have an object. Let's make this brighter. I have two objects that are moving with a certain momentum each, and then they collide and they stick together. Does that make sense? The momentum before the collision would have to equal the momentum after the collision, and they've stuck together and moved off with some new velocity. Again, it's just momentum before equals momentum after. There's lots of possibilities. I can have an object that explodes and becomes two new objects. And the momentum of the two objects, okay, has to equal the total momentum of the object before. So, which leads me to something I totally forgot to talk about earlier. Imagine a stick of dynamite, okay, sitting on this table. How much momentum does it have? None, because it's not moving. I light the fuse. Still no momentum. The whole thing explodes. How much momentum does it have? Is it a lot or is it none? It started with 0. It doesn't change. So if I looked at all the pieces of the dynamite thing that exploded, I looked at every little particle, and I measured the momentum of every little particle, and I added them up, it would add up to 0. Okay? Because the total momentum does not change, because there's no external energy or external forces acting on it. Yeah? But they're moving in opposite directions, and momentum is a vector. Okay? Okay? So here's a relatively simple situation. Okay? You've got two train cars. One of them's standing still, and one of them's moving at 24 meters per second. Let's assume right now they have the same mass. They collide and they couple together. They link together when they collide. Using the law of conservation of momentum, with what speed will both cars move off? I hear 12, I hear 24. Okay? And what has happened to the mass? It is doubled. In order to conserve momentum, what must happen to the velocity? It must be 12, right? The momentum before, here's my momentum before, mv plus mv. What's the momentum here? Well, it's whatever the mass is times 24. What's the momentum here? 0, because anything times 0 is 0. So there's my total momentum. That's what my momentum has to be afterwards. And what have I done to the mass? I've doubled it. And I've got a new v, and that's got to equal 24m, right? The new momentum has to equal the old momentum. The m cancels out, divide by 2, and you get the new velocity is 12 meters per second. The math is actually harder than just thinking about it, I think, in this situation. If you double the mass, you get half the velocity. But now let's do it. Let's do the same problem, but the masses are not the same. Let's imagine there's a bunch of people in this car. It's like, wasn't there a movie about this that just came out? Right? Okay. Unstoppable. And let's say it has a mass of 2,000 kilograms. And this train car has a mass of 1,000 kilograms. Please solve the problem now. And this one I don't think you can do in your head. I do think you actually need to write it out and see what you can figure out. But figure out if they collide and connect, what will be the new velocity of the car. So with momentum, oftentimes we will have things colliding. Whenever you're dealing with a problem with a collision, remember that momentum is conserved. Momentum is always conserved. When we get into energy next week, we will find that energy is conserved, but not always in the same way. Energy can change forms. There's lots of different kinds of energy. And that will determine the kind of collision we have. There's actually 2 general types of collisions. And the 2 general types of collisions are called elastic. And elastic you can think of as like the happy ball, okay? It's kind of bouncy. That's a general idea of an elastic collision. When a collision is elastic, momentum is conserved and kinetic energy is conserved. The second type of collision is inelastic. And that is where momentum is still conserved, but in this case, kinetic energy is not conserved. That kinetic energy is turned into some other form of energy, like the sad ball. Where did that energy go, though? Okay, into sound and heat. Listen to these 2 balls. Listen to the happy and sad ball for a second. Here's the happy one. Here's the sad one. Sounds different, doesn't it? Okay, bless you. Kinetic energy is not conserved. So when we talk about energy next week, this will make a little more sense. But just remember, there's 2 general types of collisions. Situation where we will deal with momentum, you guys, other than collisions, is with explosions. And explosions are kind of fun. We deal with them all the time. Bless you. Generally speaking, again, momentum is always conserved. And let's think about guns for a second. I haven't measured them, but they sure feel pretty similar. Okay, here's a gun, and here's a bullet. You're sitting out there, you're out hunting in the woods, you got your gun, you got your bullet. Before you fire, what's the momentum of the gun and the bullet? 0. You fire the bullet. Bullet comes out with an incredible amount of momentum. What must be true if we're going to conserve momentum? The law of conservation of momentum is true. What must happen? But it has momentum. It had none. It has some. So what must be true here? And what does the gun do? The gun must have momentum backwards. And the momentum of the gun backwards has to equal the momentum of the bullet forward. Yes. The first time. So in an explosion, again, it's just continuing to deal with conservation of momentum. If you have 0 momentum to start, you will have 0 momentum to end. Now, when we went to space, when we first started sending things and people into space back in the 50s and early 60s, there were some rocket scientists, highly intelligent scientists that were studying this stuff, that were part of the space program, that believed that once we launched a rocket into space, we would lose control of it forever. And it would go in a straight line at a constant velocity until it ran into something, Newton's first law. And their reasoning was sound. Think about it for a second. When you're driving a car, you can steer the car because of friction with the road. You're pushing against the road. When you're flying in an airplane, you can steer the airplane because there's resistance with air around it. There's something to push against. And these scientists said, hey, when we put a spaceship into space where there is nothing to push against, we will no longer be able to steer the object. It will just continue on. Because they forgot about the law of conservation of momentum. It turns out that if you can push something away from you with a certain amount of momentum, then you will have to recoil with the same momentum.
There was like a CSAT question where you're standing at an ice rink on ice skates and throw a ball backwards.
Exactly. And that is how we steer spaceships. Okay? When you have something out in space, If you eject gas out one end with a certain amount of momentum, the rocket has to go forward with the same momentum. Again, we're talking about momentum. We're not talking about velocity. We're talking about momentum. But this is exactly how we steer spaceships when they're out in space. Not because they're pushing against something, but because momentum is being conserved. Okay? Does that make sense? Okay? Finally, I know it's been a lot. Finally, you guys, we can't forget about vectors. We can't forget about vectors. Momentum is a vector quantity. Please remember that. The direction is important, okay? And most of the time we're going to be dealing with momentum in a straight line, which makes our vector analysis really, really easy. But remember, if you were dealing with multiple directions, you would have to deal with the vectors. And again, the vector components, if you added up all of the momentum vectors as vectors, the momentum would still be conserved. Couple of practice problems, you guys.
Bob. Curse you, Bob.
Curse me. Let's try this out. See if we can apply impulse momentum and conservation of momentum to these situations.